Cone problem by Sarah Showers. So basically the problem that we were given was to find the angle of the sector removed that generates the largest volume for the cone. So the basics of my cone, the radius of my circle, not the cone, the radius of my circle is 16 because my birthday is June 16th. So knowing that the radius of the circle is 16, you also know that the slant height of the cone is 16. Now here, as you can see, we are going to remove some angle that is still unknown of the circle, theta, and that will eventually produce a cone, and we are trying to find what angle will produce a cone with the highest volume. So how I am going to solve this problem. So for this problem, I chose to develop a function that determines the volume of the cone when the height is varied. Then after I figure this equation out, I can graph it on Desmos to see what height the x value produces the highest volume, which would be the y value. So using the height I find in the graph, I can use the triangle within the cone to find the angle. So here's how I went about solving it. So basically, I started with the volume equation for the cone, which is volume equals 1/3 pi r squared times the height. So then using this, I use the Pythagorean theorem. Now, when you look at the cone, there's a triangle within the cone where the radius of your circle is the slant height, the radius of the cone is one of the sides, and your height is the other side. So you get this triangle in which you can use the Pythagorean theorem. So for this, r squared, which is the hypotenuse, equals the other r squared plus the height squared. So when you rearrange this, because we're solving for this radius, it is the lowercase r squared equals uppercase r minus squared minus the height squared. So then, knowing that this is what r equals, you can plug it back into this volume equation shown above. So when I bring this down here, volume equals 1/3 pi, and now instead of having r squared, we're going to have capital R squared minus h squared times this height, because this is still a part of the equation. Now next I'm going to distribute this height, so this makes h to the third, and then distributing this makes it r squared times h. So then we're left with this. So then I'm also going to distribute the 1/3 pi to both sections of this equation within the parentheses. So from that you get 1/3 pi capital R squared times the height minus 1/3 pi height cubed. So this is kind of your final equation, and for the slant height or the radius of your original circle, mine is 16, so I can substitute that number in for that variable. So this is ultimately my final equation. So then after this, I graphed this, which you will see on the next slide, on Desmos. And so when I graphed it on Desmos, I got 2 points. Now these 2 points, x represents your height of the cone, and y represents your maximum volume that is with this height. And you know this because you cannot have a negative height, and so this is the highest on the graph that the x value goes. So knowing this, I can now find the angle. So we now know that the height for the maximum volume for this cone is 9.238. So knowing that, you are again looking back at this triangle. So if we want to find this angle, you can use cosine theta equals height over the radius of, or the slant height of the cone. So cosine theta equals height, and we know that is 16 because of my birthday. So then you do cosine inverse the height over 16. So we still need to know the height, which we found above is the maximum is 9.238. So cosine inverse 9.238 over 16 gives you a final answer of 54.7 degrees to get your maximum volume. So basically, in conclusion, from this, it concluded that the angle needed to get the maximum volume for this cone is 54.7 degrees. This angle gives you a maximum volume of 1,650.96 units squared.